So we've introduced this whole framework of Lorentz tensors. Tensors in the universe where the only coordinate transformations allowed are Lorentz transformations. And now I want to show you what this does for us. And the first example that we're going to do is Maxwell's equations. So Maxwell's equations, you're used to from a form like this. I can never remember all the signs, so I'm just copying them down. Curl of B minus the time derivative of E is J. And divergence of E is rho. Now, I'm using different units. There might be a 4 pi epsilon naught. I never remember where those go. It's just a choice of units. So in this case, we're using units where it's just the charge density rho. The curl of E, then, I think this is supposed to have opposite sign to the first equation, plus the time derivative of B is 0, and the divergence of B equals 0. What? It doesn't matter. It's some units. I don't know the name. So these equations have a symmetry that you probably don't think about very much, which is rotational symmetry. Okay? If I do these are Cartesian coordinates of the vectors, but if I do a rotation and I express E and B and gradient in the new coordinate system, automatically the equations take exactly the same form. I could put a prime on every quantity to mean the rotated thing, but it's automatically going to take exactly the same form. I'm not going to generate new terms by rotations. And that's basically obvious and not emphasized because the whole point of drawing these little arrows above symbols and introducing vectors and telling you that you're only allowed to do divergence and curl as derivatives of vectors is because those are the only operations that play nice with rotations, right? If I had written, if I had added a term plus dx of E, that's not going to play nice with rotations because what is x, right? Like the God-given direction that way, it would have a preferred direction in it. Okay, so Maxwell's equations don't have anything like this. That make reference to a preferred orientation of space. And the mathematical expression is if I worked very hard and did a rotation and wrote the components again, I would get the same exact equations. Okay? So what we say then is that the rotational symmetry is manifest. In the notation. So manifest just means obvious. In the notation, the little arrow and the curl thing and the divergence thing. Like these things are defined so that rotational symmetry is always preserved. Okay? Now there's another symmetry of these equations which is really not manifest, and that's Lorentz boost symmetry. Okay, so this is part of how special relativity was actually discovered, thinking about these equations. So on the other hand, Lorentz boost symmetry is not manifest. It's just you can't see. It's totally mysterious. Like, you have to work it out. And so if you go back to the definition, how you're going to introduce these things like charges and currents and how they're going to source, or rather electric and magnetic fields, we don't need to worry about charges and currents. If you go back to the definition, electromagnetic fields in terms of some physical operation, like motion of a test charge or something like that, and you ask, what are my new electric and magnetic fields in a new Lorentz frame, you have some very complicated expression. So, for example, if we introduced E prime equals gamma E plus B cross B minus, we're never going to use this formula, but it's good to write it down for effect so you can see how complicated it is. This is V hat, the direction of the velocity we do the boost. V hat, so we introduce these two things. B prime is gamma B minus V cross E. minus gamma minus 1 b dot v hat v hat. So these are the formulas, and you can go look in your E&M textbook for how you express E and B in a new frame. And they're quite complicated. But the claim is, if you plug them in there and do a lot of work, calculate, you'll get the same equations with primes. That's it. You just put a prime on B and E. That is not obvious. And that's a problem, because you have a question?
Yeah, you also have to do space and time.
Do space and time derivatives under a Lorentz transformation.
Yeah.
That's true. Yeah, d by dx will have some behavior because there's an x there. So there'll be a prime on the derivative operator as well. Yeah. So you go through that whole exercise. Right, we talked about how taking a derivative adds an index. So it's the same idea. So you go through that whole exercise, and you find the same equations with a prime on EB and grad. And so that's an issue because that might be an important property of these equations, right? If you're writing down like a new theory of physics, you really want to understand the symmetries present in your equations. And the tensor notation is going to do this. So what we'll demonstrate now is that if we introduce this field strength tensor that encodes the electric and magnetic fields in the same way that we talked about last time, then Maxwell's equations are just tensor equations. And then you know just from the notation, because we established all these rules of notation, that they'll hold in any Lorentz frame with the same form. All right, so let's see how we do that. I need transformation laws for J and rho as well in this case. I won't write them out, but since I put them in, they will also have transformation laws. So what we want to do is start translating these Maxwell's equations up here into a tensor notation. So the first thing I'm going to point out is that for two vectors, A, the cross product, and I'm going to write it in vector notation, the ith component is epsilon I j k. This is that Levi-Civita tensor we introduced last time. I guess I should probably make it lower since our vectors are conventionally upstairs. Let's do I j k A j B k. So now I'm raising and lowering with delta ij, which is the spatial metric. And so the convention is that spatial indices I and j run over just 1, 2, and 3. Okay. So that's just a nice way of writing the cross product so we can start getting closer to the index notation. Yes? Sorry?
When we use the four-component Levi-Civita tensor, if we are to like raise components,
Yeah, you'll flip signs if you're using the Minkowski metric, A to mu nu.
we'll actually flip signs
Mm-hmm.
sometimes.
Yeah. Okay, so this is a nice notation. So now what we can do is we can take this equation here, curl of B, I think that's the one I'm starting with, and we can rewrite curl of B. We're going to write that as epsilon ijk. Okay, now I am going to lower indices freely on my vectors and so forth. So del j bk. So that's the first term here. That's the ith component of the curl of B. And then the second term is just the time derivative. And I'm going to write that as the zero derivative because, remember, Okay, because remember our convention is 0 is the time coordinate, and we want to get close to index notation. And so it was the time derivative of e I, and that was just equal to j I. Okay, so that's one equation. Let's just keep going. So the next equation is divergence of E equals rho. By the way, I have a cold. I'm COVID negative, but I tested this morning. But if you hear me sniffle, do not be alarmed. Everyone else in my family has already had it. I was the last one. So divergence of E equals rho. So how do we write divergence of E in index notation? Well, that's just del I E I. And rho is just rho. But with a bit of knowledge of the answer, instead of rho, I'm going to write it as j upper 0. What's j upper 0? Well, I'm introducing now j mu equals a vector, 4 vector composed of j upper 0, which is rho. I guess I can just write it as rho. And the ith, the 3 spatial components of the current. Okay, so we're sandwiching the charge density rho with the current density j in a 4 vector. And you'll see why, because that's what works. Then we have to keep going. So the next equation on the list at the top of the screen, curl of E. So same idea, epsilon I j k, but now it's del j e k plus del 0 b I equals 0. And then the last one, divergence of b equals 0. Del I bi equals 0. Okay, so all I've done is switch to index notation. And now is where that field strength tensor comes in that we wrote out last time. If we were clever, we could notice that this thing is becoming a good space-time tensor if we introduce, and last time I wrote it as a matrix, this time I'm going to write it as F0I is the electric field. So this is just my creation of a field strength tensor F mu nu. The 0I components are going to be EI. It's an antisymmetric tensor. So that's going to be the same as minus Fi0. And then, yep?
So like you switched the t to 0, right?
Yeah, just notation.
But that's minus t, right?
No,
It's not minus t.
there's no metric. I haven't put any metric of any.
X super mu is minus t x y.
This is a down, no, so we'll never lower the index on the coordinate. I will hopefully never write this, because coordinates are only like vectors in Lorentz frames in flat spacetime. So I will,
The first element of x super mu is minus t.
no, it's plus t, absolutely. That's, yeah, it's just x mu just lists the coordinates. Okay, and then the funny components of b that I wrote down last time can be expressed as f upper ij is epsilon I j k bk. And that is then also equal to minus fji. So this now defines my field strength tensor F mu nu. Whoa. I need to double click to move it, but if I do it too fast, it scrolls in. Zooms in. Okay. So this thing together defines F mu nu. I might have wrote it lowered indices last time. It doesn't matter. We're now freely raising and lowering indices using the metric. I just have to make sure I got my signs right in however I define it. Okay, so we have the 4 Maxwell equations here, and now we need to start using our field strength tensor So let's see what we have here. Well, I've got epsilon ijk something bk. Well, over here I have epsilon ijk bk, right? So this thing in red is going to be the same thing as f ij, but there's a derivative here. So if I imagine pulling the epsilon in, this will become del j fij. That's what happened to the red term. Okay. So you see that by, did I do something wrong?
Well, no, I just want to check. So F00, though technically we didn't actually express it.
It's 0 because f is antisymmetric. Good point. So strictly speaking, I should say it's antisymmetric. So now f00 has to be 0 because it's antisymmetric. Thank you. Yes, thank you. Don't know why I do this stuff.
You don't want to make it whole zero.
Yes, thank you. That is important. I appreciate those corrections.
That would be a very fun
I mean, Maxwell's equations would be true for no source and current, right?
Yeah,
Okay.
don't worry.
All right, so anyway, this one became del j fij. What happens to del 0 ei? Well, I can't do much yet, except I can plug in. E upper I is f upper 0 I. So I want more colors. I got to get good at this. This is the whole point of doing it.
What will happen when you click on the rainbow?
I want this to look green so you can see the correspondence. Okay, and then ji is just ji. Okay, so that's what happens to the first equation, but we're going to do it to all of them. I guess the second equation, might as well do it. No, let's finish working on this one. So let's work on this equation star. And so now we just notice that we have a, I need to flip the indices. We're almost at a sum here. So I'm going to change this from 0i to I0. So I'm allowed to do that because f is antisymmetric. And then this I'm going to leave del j f ij. I'll just leave this as ji. And then, now, notice this is a sum from 1, 2, 3. But this is the missing 0. So what I mean by that is this left-hand side is actually del mu f I mu. Right, think about it. If I write it out, this is a sum over 0, 1, 2, 3. So the first term where mu is 0, well, that's just the term on the right here. And the next terms where mu is spatial, I could call it j equals 1, 2, 3. Well, that's just the term on the left. Mm-hmm.
Is d0
Means time derivative.
ddt or
Yes.
-ddt?
No, ddt.
Okay.
The derivative is naturally downstairs.
Okay, we just never have.
So d, the definition of d mu is d by d upstairs mu. So I'm never going to lower the index on the coordinate, and upstairs mu means just t for x upstairs 0. So d downstairs 0, d0 is just d by dt. Okay, so that's what happened on the left-hand side. On the right-hand side, I still have ji. And that's all for that equation. Now let's do the next equation here. Let's do this one. So what can we turn that into? Well, that's del I ei is f0i equals j0. And to make them look similar, I should flip, I believe I should flip. I do not need to flip. Yes. So now the point is, this is the spatial components of an equation. And this is the time component of the equation. And the equation is del mu f nu mu equals j nu. because here we have nu equals 0. This is the nu equals 0 component of that equation, and this is the nu equals I component of that equation.
And it goes through everything except for I equals 0, which would just be 0. Yeah, this here is.
I equals 0?
But like I just goes from 1 to 3.
Oh,
I
yeah,
is
that's a
1
missing
goes
step.
from mu.
That's a good point. I should first change this to del mu f 0 mu equals j0 because f0, 0 equals 0. Thank you. These are things that are like, I've done it so much I don't notice these steps, so I appreciate that. So that is conceptually a missing step. Okay, and then the two equations are the nu equals 0 and nu equals I component. Okay, so what we've done is combine the first two Maxwell's equations. So these are the first two Maxwell equations. And it follows the rules of tensor notation, right? I've got one downstairs mu, one upstairs mu. They're summed over, and I've got one upstairs nu on each side. That's a free index. So we know instantly that those two equations by themselves, those first two equations, are invariant under Lorentz transformations, just from the notation. We were able to write it in a way where the notation is consistent. And now if you want to check, you can plug in all your gamma matrices, lambda matrices, and they'll line up, and the inverse matrices will cancel out, and so forth. And so you can write, this takes the same form in every Lorentz frame. Okay? So I'm doing this like really slowly, but conceptually, this is basically what you do to do physics in curved spacetime. You take laws of physics in flat space, you write them in an invariant looking form, and then you say, okay, this is going to hold in curved spacetime too with the same form. So we haven't done that last step yet, but this is preparation for it. Yes?
I wanted to ask about F. Like obviously here you were just like, this is the field tensor.
Yeah.
Is that how like it was come up with? That somebody was just like, this works?
I don't know historically, but I think this works is as good an argument as you're going to get at the classical level. You can, when you think of quantum field theory, you can think about the gauge symmetry of the vector field and spin one field. There's another way to get it, but I think classically you just have Maxwell's equations and you notice this is the way to write them so that the symmetry is manifest. Yeah?
Are we going to go through showing that the other
You're going to do that on the homework.
equations work?
So on the homework, you're going to prove that the third and fourth Maxwell equations become the following: del alpha f beta gamma plus cyclic permutations del gamma f alpha beta plus del beta f beta gamma alpha equals 0.
And it's problem set 3.
Do, yeah, the material, so I always, yeah, the problems that do not Wednesday, but next week.
I was going to say I submitted one doing Wednesday last night.
Yes, no, this is, I try to cover all the material for next week's homework on Tuesday and Thursday. Okay, any questions? So now we know Maxwell's equations are invariant under Lorentz transformations, and we've had some exercise in converting notation to the notation we're going to be forced to use in curved spacetime.